it away.
Okay, thank you so much. So, good morning, good afternoon. I'm going to actually, I'm very glad that Andre went first because I'm going to be touching in many of the points that he explained, and there are some many, well, complementary issues that we're going to be discussing about. So, okay, so I'm going to talk about a bit of an introduction of what it's could be maybe the basics of magnetic radiometry, if we can ever say anything basic about that, which is not basic at all. Then a bit on the process. I'm going to touch a bit on the processing, which is normally not what I do. The contractor and Supracon and Diaz, they are dealing with that. But then we're going to spend some time dealing with gridding. Rick was talking about full tensor interpolation that's being done by Intrepid. So I have two, well, when I gave this presentation in SAGA in 2024, we just have this paper coming out, the full tensor magnetic radiometry, the geophysical prospecting one. And this paper shows very interesting results to how to go from tensor components to TMI. So I'm going to be touching on that. The main update since last saga is that Akshay and all his magic, he managed to get this paper out, which is TensorWeave 1.0, which is an algorithm, a neural net algorithm, based algorithm to interpolate full tensor data, and it's open source. So that's going to be, it's definitely a major improvement on where we were before. And then I want to touch on what to do with all those components. Andrew was showing great results on how to use the components in model vision to model the data and try to separate the different kinds of sources. And so all that, of course, it's great use of the data. But there are many complications. We're going to, well, it's too bad that that system that they were going to fly, that the VS was going to fly with a spectrum of full tensor gradiometry with a couple of cesium vapor sensors. It's too bad that it's not flying because that's exactly what we need. As we're going to see when you go do the integration from tensor components to vector components and then go into the total field, you need those long wavelengths. So in short, well, full tensor magnetic radiometry has been flown commercially for quite a while. There are still some unresolved questions. Many people are still wondering, is it worth it? It's definitely more expensive than flying regular total field. And so the question remains, shouldn't we just go with a drone system instead? We can fly much lower at a tighter spacing and then produce a total field. But it wasn't the conclusions from Andrew's presentation is yes, you from total field you can get tensor components, but since you are dealing with FFTs, the data is not necessarily going to be the same quality as you measure it. Then the other thing is, yeah, we have 5 components. What to do about it? So yeah, what can I do with all those things? So in terms of the system has been around since the 2000s, and it has been slow to start flying commercially because it's complicated. The sensors are very small sensors that you need to align, and the main thing is, yes, you need the cryogenics, you need to cool all those sensors, and that involves extra cost. It's not just going with a magnetic radiometry uh, like we normally do. And then we know that the data is better, but they're still not clear what to do about it. These are images from a paper by Jonathan Rudd, 2022, where she shows, this is a survey where, yeah, he shows all the components, great data, and then he compares a BSET set to more or less a TMI 1VD because they are more or less similar, which is right. They are more or less similar, but what do I mean by more or less? Can we get a bit closer than that? Um, so in terms of acquisition, so the system was designed at the Leibniz Institute of Photonic Technology, IPHT. So you have two instrument packs. One is the cryogenic, where it contains the squids, and it has 6 gradiometries that measure the magnetic gradients. You have 4 magnetometers that measure the field components that you use for compensation. And then you have another smaller pack that has all the data acquisition and GPS and inertial navigation and the radar. So it's a complex system. And like I said before, the bulk of the processing is done by the contractor. So what they do is they have to take, of course, they need to synchronize all the ancillary data, so all the GPS, the inertial navigation, altimeters, squids. Then there is some post-processing of the GPS and inertial navigation systems. And you need to decimate it down to 10 hertz. This data is sampled at much higher rate. I'm not sure what is the rate they're using, but it's much higher than 10 hertz. And then there are processes of calibration, discrete magnetometer signals, and then there's another process of balancing, and then the composition of those into the tensor, and then you need to rotate from the body frame to an actual well. So yeah, so from the reference system of the aircraft or the sensor to Earth, Earth center coordinate system using Euler angles. So at the end of all this, which is a very intensive processing, you end up with we have 5 independent components. So because remember that because of the tracelessness, bxx plus byy plus bzz has to be 0. So with 2 of them, we can get the third one. So what can we do from that? So this is where the first thing that comes to mind is gridding. How we're going to do this gridding. There are 2 possible ways to do it. One is to do what we call component-wise interpolation, or it's just grid the components independently. So you have 5 channels of data, you treat them like it was any data, and then you grid them independently, and then you produce those 5 images. So that's one way to do it. In order to do that, you can use the standard minimum curvature that we have been using for years, or you can get into fancier interpolators like the radial basis function interpolator that I'm going to talk a bit, which is a better interpolator. But still you are using the components independently, and then from that you can reconstruct the tensor. The other option is to do full tensor interpolation. And this is what Henry was mentioning, that the Intrepid, and this Fitzgerald in particular, he's being kind of the leading source of all that information. And so the whole idea of that is do an eigen decomposition of the data into eigenvalues and eigenvectors. So the eigenvalues, you interpolate them with any interpolator like minimum curvature, RREF, etc. The eigenvectors, you convert into a quaternion, and then you can use that SLERP algorithm that Andrew was discussing before. And for using those 2, you can get into the tensor. The thing is, yeah, well, if you don't have Intrepid, what do you do about it, right? So RBF, what is it? So it's an extension of a polynomial spline. So the underlying surface is a sum of scale polynomials. So the kernel function is a radially variable function centered on each of the points. So for each point, you are going to do one of these expansions. And then you use this interpolant so you can reconstruct the data. So depending on how many points you use in your expansion, obviously it's how good your solution is going to be, but of course it's going to need more resources. So how does RBF compares to minimum curvature? So RBF utilizes these radial functions, and then the surface is fitted by finding a smooth function that minimizes the error between known data points and can be truncated. So you use smaller number of neighbors to calculate that kernel and the weights. On the other hand, minimum curvature, what we do is we minimize the second derivative of the surface and we try to fit a smooth curve into using all the data. So how do they look? So this is some data that we were allowed to use. It's a magnetic gradiometer survey flown at 50-meter line spacing. And remember, one of the things is that if you use full tensor interpolation, you can go to 1/8 of the line spacing because you have more data. So that is you use full tensor. If you use independent components, you should go to only 1/4 or 1/5 of the line spacing. So for this situation, we have 50-meter line spacing. We went with the minimum curvature, we went to 12.5 meters. And with the RBF, since it's a better interpolator, we were able to push the envelope a bit more and we went to 1/8, so we went to 6.25. So and this is B set for those cases. So in this case, you see, well, yeah, at this scale, they both look okay. I don't really see a great difference. The main difference would be that with RBF, I'm getting to a smaller cell size without the need to go to full tensor. So let's do a bit in terms of full tensor interpolation. So we're going to do an eigen decomposition into eigenvalues and eigenvectors. And this is one of the results that Akshay derived some time ago when we were working on a few things is, do we really need full tensor interpolation? So here, the idea is that this on the diagram on the left, these are your input tensors. So you see the ellipsoids are showing you the direction of where the tensor is going. So you have these two kind of east-west, and then in the center it goes kind of north-south, and then at the bottom it goes east-west again. So if you use full tensor interpolation, this is what you get. So you are able to follow that pretty well. Whereas if you use component-wise interpolation, so just single components, the result is not that good, especially in the center parts. So you see that swelling that's happening there. However, when we are for the kind of data that we're using, it's normally not that common to get this massive change in the ellipsoids going from pretty much a 90-degree. If you put a smaller rotation, so in this case, it's something like 15 degrees rotation. These are the results that I get from component-wise interpolation and full tensor interpolation. So they're pretty similar. And that's why we can get away with just component-wise interpolation most of the time. However, once again, and I'm going to insist on this, is that when you use component-wise interpolation, we're going to get to only 1/4 of the line or 1/5 of the line spacing. These are some results of what we got with full tensor interpolation, and for this case, we used Intrepid. So the same algorithm that Andre was discussing before. So this was, I'm showing BZ set. So for this, we use full tensor interpolation, and we are at a 1/8 of the line spacing, so 6.25. This is minimum curvature, just interpolating a single component, 12.5 grid cell size, and then the RBF at 6.25. So once again, at this scale, I don't really see a massive difference in this area where you have high gradients. I would argue maybe that the full tensor looks a bit cleaner. the minimum curvature and the RBF both should start showing kind of east-west trends in both sides. So it looks cleaner, but it's not a night and day thing. And this is a new result. This is from Akshai's paper, actually. So because I wanted to show what he's been working on. So this is another survey. So this is the actual data. So this is BXX, BXY, BXZ. The middle one is the result of an RBF interpolation using a desampled data set. So you see the line spacing is very fine. So that's the actual data on the top. The middle and the bottom one are interpolated versions with a desampled data set. So we are using less data points to see what we get. This is RBF, and you see it's kind of noisy, and this is the result of Akshai's tensor weave. So this is the full tensor interpolation that he's getting, which is much, much cleaner than we are getting with the RBF component-wise interpolation. So going back to the previous data set, so yeah, and similar exercise. So desample the data. So this is the original data plotted as points, no interpolation. So this is BZZ, and this is if I desample that to 150 meters and I grid it at 1/10 of the line spacing. So really pushing things. Yeah, and of course I'm going to get lots of aliasing because yeah, I'm going to 1/10 of the line spacing. And this is the result of minimum curvature, and this is the result we got with full tensor interpolation. So this was using Intrepid. Yeah. So yeah, both of them are suffering from, yeah, they're not able to resolve those trends fully. So in terms of gridding, one is that on paper we are able to get away with component interpolation. However, we should behave and keep ourselves to 1/4 to 1/5 of the line spacing. Otherwise, we're really going to create alias the data. RBF is a much better interpolation than minimal curvature. And by the time I gave this presentation at SAGA, that was not available unless you were a Python person. But now in geoscience analysts, they have an RBF interpolator routine for those who are using that. So now let's see what do we do about those components, or how can we go from from components, tensor components to TMI. Okay, so this is and Gordon is there, so he's going to be happy about this. So what are we measuring here? So the anomalous field is a vector defined by T minus F. So this is the total field. Well, yeah, this is what we measure, and this is the IGRF, or the Earth's magnetic field. So the difference between those two is that delta F in vectors. Um, however, if you do the total field anomaly, it's a scalar defined by the norm of this minus the norm of that one. So when we're doing scalar surveys, and that's what we call delta T, the norm of that minus the norm of that. And that is pretty much what we have here in red. So if I take the norm of T minus the norm of F is the red segment. However, since this vector is usually much smaller than F, because the Earth's magnetic field is much larger, we normally can do an approximation. So this is coming from Blakely. So if you do T minus F in norm form, it's pretty similar to do this dot product F projected into delta F divided by the norm of F. So in other words, the unit vector of F times the dot product with delta F. And if you substitute, yeah, this one into here. So this is what we have for delta T. It's actually this IGRF divided by the norm of it, dot product T minus F. And that is the light blue. So you see the light blue is not necessarily the same as red. Most of the time, we treat them as the same, but they're not. And this is the key. If you have remanence, those two vectors are going to be different. So if your magnetization is mostly induced, these two are going to be very close. If you have remanence, they can be very different. And then what is the length of that vector? The length of that vector is this is what in Australia they normally refer to it as big T. So it's the length of that. There is a paper by Stavrev and Girovska where they define this, and I can't remember their definition, how they call this, but it's defined there as well. But the key is that when you take these components and then you get the length of that vector, so by doing this is not total field. This, okay? So in summary, in order to get total field, we need to do this, what I have in this equation 4. And if you have your tensor components, you convert them to vectors and you compute the norm of that vector, that's what we are calling here big T. So they are not the same thing. So I'm going to show you some examples. So, and this is where, yeah, okay, so bear with me for a second. So this is total magnetic intensity that I computed using this equation 4 for that data set using the tensor components. This is what I got using minimum curvature on, so this was in the full tensor interpolation. This is just using minimum curvature independent components. This is using RBF, and this was an existing scalar survey at 30-meter lines grid cell size. So it was 150-meter line spacing. This was flown at 50. So of course I have 3 times as many lines on the one on the left compared to the scalar. But the difference is astounding. So these linear trends here are showing way better than in the scalar one. On the other hand, yes, this is great, but if I have just minimal curvature on independent components and apply this equation 4, I can also get a decent result. The main difference is that the cell size is going to be constrained to 1/4 to 1/5 of the line spacing, 12.5, instead of going all the way to 6.25. But I can get away with it, and I can get a decent result. So this is total magnetic intensity. And then if I use the other equation, equation 5, this is what I'm calling big T. And if you look this map and this map, you're going to say, yeah, but they are the same thing. Well, if you compute the difference between both, they're not quite the same. There are some slight differences between both. The differences are small, but the importance of this for exploration and these differences are in areas where there is remanent magnetization. So this is giving us a way to find remanence magnetization. This is another example where I have tensor data, and I didn't have the database, so they gave me just the independent components gridded using minimum curvature, and I put them into my equation, and this is what I find. And this is the same area flown with a scalar survey. And then look at the definition of those dikes. It's much clearer. So even if I just use a component-based interpolation, I'm getting a very decent result. Some complications. It's how to do the integration. And the integration, it's, Andre mentioned, yeah, well, we don't know the long wavelengths. That's definitely a problem. These are some equations from a PhD thesis from Vasiliu, 1986, University of Calgary, where he had this transfer function. So how to obtain the vector components from tensor components. So this is, you can integrate using only one component or two components or three components. Yeah. So you have all those three, or you can also use just a vertical integral filter from your TZ set. And these are the different results that I get. So in this case, I use three components to integrate in order to get to my V set. Here I use two components, one component, and this is the vertical integral. And you see they're all over the place. So which one is the real one? And that's the problem. We don't know the integration constant. There is another problem, is the FFT. So was using 3 components, and this is just a vertical integral. And you see, this is not just a trend in the data. In fact, I did this in GeoSoft. When you do this calculation in GeoSoft, you need to do the grid, the preparation of the grid. So you need to expand it. So you do the expansion and the padding of the grid. So if you use just the default parameters, this is the expanded grid. So you see the grid has to be periodical to a certain power of 2 and so on. So this is what you get normally. But in this case, I use a cosine of roll-off of 20 cells to stop all that craziness that's happening around that. Once I do that, I get a much cleaner result. Yeah, so careful with that. The base level. So the Henry was mentioning this. Yeah, where is the base level? This is a case for Geiger in Germany, where I have 2 gravity gradiometry surveys, one in 2014, one in 2015, with different processings. And we also have a scalar survey, and you see the base level. So this is total field derived from that. Can be anywhere. We don't know where the base level is, and that's a problem. And even if you apply a DC shift, yes, you can get things to more or less line up, but the problem is it's not just a DC shift. In this case here, you see there is a trend in the data as well. So there's a slope. So unless you measure it, that becomes problematic. So this is the same for components. So the final thoughts are, is it worth flying tensor data? So what I have done here is to go from tensor components to total field. And once I produce a very clean total field, I can go into the standard interpretation products. In this case, I'm showing a tilt derivative. And the difference becomes astounding, because this is the tilt derivative that I computed using the full tensor interpolated grid that I used to generate my total field. This is the one I was with minimum curvature on components. This is RBF, and this was the existing scalar. So if you compare the full tensor interpolated versus this scalar, there is quite the difference. This yeah, so this is so this is the same data set, but I'm showing a zoom, a close up. So this is the tensor derived TMI, this was the scalar, this is a 1VD in the center, and then the tilt derivative on the right side. So yes, total field. So even if you just look at the total field, there are many other advantages, like for modeling and inverting the data. Of course, having more components is going to give you a much better definition of things, and you're able to separate different cases, like on that model that Henry showed before. The other thing is, yeah, well, is it worth flying tensor compared to a ground data or a drone survey? This is a case in Germany where we were very lucky to have, we had a ground data scalar survey done at 5-meter line spacing. Then we have a drone survey at 10-meter line spacing and height. Then we have the tensor mag with 50-meter line spacing, and this was helicopter scalar total field, 100-meter line spacing. The flight lines are there on the top. And what I'm showing here is mean curvature. So rather, because when we looked before at the total field maps, yeah, they look similar, and then you can argue one way or another. But once you go into higher end products like curvature, this is where the tensor shines as well. Because, yeah, of course, I have more data in this tensor data set than on the scalar one, but the curvature derived from the tensor data, so this figure C is much cleaner, it has way more texture than the scalar airborne. Then the drone, the problem of that as well is that since you have much more data, well, it's more prone to noise, high frequency noise as well. So Yeah, and as a result, I still believe that this one is better even than the drone and the ground survey. And then another thing, so going back to Akshai's paper here, is that using his algorithm for full tensor interpolation, another beauty of it is that you obtain, you interpolate the tensor, but it also gives you vector components. So this is, so again, this was the data. These were the vector components using just RBF, and this is the vector components that he derived from his algorithm, which are way much cleaner as well. And once you have these vector components, you can start playing games with remanence and things like that as well. So in summary, tensor data is definitely worth it. Is it expensive? Yes, but depending on the exploration the program, yeah, it can definitely make a difference. Full tensor gridding, we can get away without it, but you should be using it if you have tensor data. There is an interesting development that, that's something that David Pratt from Tensor Research has been working on, is try to, from total field, get tensor components and then using all those inversions. But like Andre mentioned before, yes, it works, but it's not going to be the same quality as the data that you can collect with these systems. What to do with the data? Having these additional components is always going to help for constraining models. So if you have model vision, you can use all those components to, when you are inverting, you can invert. And if you're trying to fit all those components, you are able to separate between, for example, two different models as well. And what else? We need, ideally, we want to measure those long wavelengths. I think we went through this when the FTG, well, the gravity gradiometry system was starting as well, that we initially, the contractors didn't want to add a regular gravity meter there, and eventually they end up saying, yes, actually, we need that. So we need that as well. And with the FFT, have to be careful. Don't just rely on those defaults and press the button. You, have a look at your prepare grades, because that can kill the processing. So thanks everyone. Thanks to SAGA for the invitation, and Vale Base Metals gave us permission to publish some of this data, and then Tensor Research, Dave has been great with software as well. If you have any questions, I'm here.
Wonderful. Thanks